let's move on to the next speaker. The next speaker is Ekaterina Berseneva from Exeter University. And maybe Ekaterina, you can try to share your slides.
Yeah, hi everyone. So my name is Ekaterina, but shortly it's Kate. And
Okay,
no,
okay.
it's both fine, both fine. So sometimes it's just you can see both. So let me try to share my screen. My computer is playing tricky games today, but I hope it will start soon, stop soon, because
Okay,
otherwise it won't go further. So do you see my screen?
right. We see your screen and everything is fine. I will give you 5-minute notice if that's fine for you.
What?
5 minutes before the end of the time, like 40 minutes in,
Yeah,
and
absolutely
tell
fine.
you 5 minutes left. Okay, so we have our next speaker, and the title of the talk is Quantum Electrodynamics and Relativistic Corrections of the G factor and hyperfine structure splitting in highly charged ions. So go ahead. Thank you.
Yes. So, hi everyone. My name is Kate or Ekaterina Berseneva, and as you see, I am representing University of Exeter and STEM Global and in STEM Institute, and I will talk about it a bit more later. And today, I will give you a brief introduction into the world of quantum electrodynamics and relativistic corrections of the G factor and the hyperfine structure splitting in highly charged ions. So I will be talking briefly about the methodics that we use, theoretical, numerical, and I will also introduce you to our results that we obtained together with the experimental group. So, what is University of Exeter? University of Exeter is a part of the Russell Group. It's one of the top 10 universities in UK. It's have a extremely well scientific impact and performances, and probably you all will know it for the Graphene Center, for the AI and Data Center. So it's even third in materials and engineering and in technology, and it is in the southwest of England, if you see it here. So it's a very, very, very nice area, and we're very happy being there. So what is the STEM lab? So I guess it was on the first day of the conference, the leading researcher and the professor Anna Baldacheva, she was talking more about the STEM lab that she actually founded. And what is STEM lab? Our motto is from smart materials to smart things. And we talk about the fundamental research and development of new nanomaterials and industrial implementations and testing. So we're really looking forward not only for experimental, theoretical, and scientific results, but also we want to try our best to help students, researchers, early career researchers, and professors, so everyone to find the road to commercializations and market implementation of their project. So our lab is divided in 3 parts. The first one is Smart Nanomaterials Lab. I won't be really talking about that today, but they work about on the new nanomaterials, multifunctional materials. The second lab is Optoelectronic Systems Lab, and it's also about nanomaterials, photonic devices, flexible devices, energy harvesting, sensing. And the third lab is the lab that I am leading, is machine learning and AI lab. And we're doing their extremely bulky, complicated calculations. And now we do their calculations on G factor, but at the same time, we work about the AI integrations on fintech and healthcare. So as I mentioned just a few minutes before, I'm also represented by the InSTEMR Institute, and it's a new institution. And please go to our website, join our Scientific Society, where we talk a lot about support of students, about support of science, about bridging science and technology. So it's about science, technology, engineering, mathematics, and medicine, and art. So which is rare, and we're trying to bridge all of this together. So let me shift further to my talk, And just 1 second, let me unshare and then share fast my screen, because there is some sign of my computer that asked me to do that. Just 1 second, sorry. So where are we? We're here. Here is my presentation, and I'm coming back to share my screen. So yes, you see my screen. So why are we actually interested in our research? And it's very easy, because we work, as I told, we work with experimental groups. And as I told you before, that over the past decades, there has been a significant development of computer technology and new theoretical methods. And it resulted in the process in study of various physical properties of atoms and molecules, and of course, ions as well. The comparison of theoretical data with high precision experimental data gives a possibility not only to interpret the results of the measurements that are done by the experimental groups, but also for testing a number of fundamental theories and the precise determination of fundamental constants. As you see on my presentation, it's you can test such fundamental constants like mass of the electron. And of course, the determination of fundamental constants like the mass of the electron and the fine structure constant with high accuracy in highly charged ions comprise an ultra-sensitive tool for testing the quantum electrodynamics effects in the strongest electronic and magnetic fields. Experimental groups, they are mostly interested in our calculations when we talk about the magnetical optical traps, because when you trap the particle, you need to know you need to know the coefficients of hyperfine structure splitting. So let's move forward and talk about what is G factor and what is the hyperfine structure. They have similar nature. They both come from interaction with the magnetic field. The G factor comes as a result of the interaction with the external magnetic field, while the hyperfine structure comes as an interaction with the magnetic dipole moment of a nucleus. G factor at the same time could be described as a dimensionless quantity that is used to describe the magnetic and angular momentum of the particle. It could be electron or other particle, but to describe the hyperfine structure splitting constant, let us imagine the simple example of hydrogen-like ion. What is hydrogen-like ion? It's an ion that only has one electron that orbits the nucleus. So both proton, the nucleus, and electron, they have a spin, and that could be either up or down, right? So normally there is an electron orbiting on one orbit. That's what we know from the theory, but actually nucleus and electron, they have spins either up or down. And in this simple model, there could be 4 positions, 4 possible spin states. And all these 4 possible spin states could be described as ground states. However, all of these ground states, they will have a slightly different energies, and actually we will never find our electron on the energy that we're supposed to find it. And this small shift of energy levels is actually called the Zeeman split. So we see that there could be different ways where we find our electron. And we can also represent it in the way that the Richard Feynman represents it. So what is the G factor, how we construct it from the mathematical sense of view? So it's a kind of bulky formula where this value is a direct value. It's very easy to calculate. Then there is this little electronic interaction, which is hard to calculate, because imagine if you don't have a hydrogen-like ion, you have a lithium-like ion or whatever, calcium-like, and then you have 2, 3, 4, 5, 7, I don't know, 10 electrons, and they all together, they come into interaction, and so they affect this energy split. Then there is also one electron QED correction and screened QED corrections and contribution of nuclear size and nuclear recoil. And you can also represent it in the way of the Feynman diagrams for 1 electron corrections, 2 loop level, and so on and so forth. So the term that actually we are working on is this an interelectronic interaction. And the first term, you can calculate it analytically, but the further you go, the more photon exchange you have, the less it's possible to calculate analytically, because it would take you years, or maybe hundreds of years. And QED screening, the further corrections is QED and electronic interactions mixed terms. Self-energy, vacuum polarization. The hyperfine structure splitting could also be represented in the mathematical way, where what actually experimental groups, that what they need from us are these coefficients A and B, so they can tune their experimental equipment. Of course, there is a Fermi energy, there is one electron relativistic factor, there is a correction for distribution of nuclear charge, there is a correction for distribution of magnetic moment over the nucleus, worldwide scope. It used to pose a lot of problems to calculate it, but then quite recently it was proved by the Shabayev group from the St. Petersburg State University how to easily calculate it by the distraction of the term from the lithium-like ions to hydrogen-like ions. So as you see here, here is fine structure splitting picture, and here's a hyperfine structure splitting picture. So what do we do actually? What do we do, and how is it different? What we actually do is we use the calculation at first by the Dirac-Fock method. The general scheme of the relativistic calculation of the electronic structure of atoms or ions, it doesn't matter, by the Dirac-Form Sturm method, that can also be reproduced in a relativistic fashion. First, the single electron wave function are calculated by Dirac-Fock or multi-configuration Dirac-Fock method. Then the second point is, for each value of the relativistic quantum number kappa, the Dirac-Sturm orbitals are derived. The set of Dirac-Fock orbitals previously obtained for occupied or partially occupied states is supplemented by virtual Dirac-Sturm orbitals. So we take Dirac-Fock and we add virtual Dirac-Sturm orbitals. This set of function forms the single electron basis, which is necessary in order to carry out further calculation using the configuration interaction method. The third step is we take into account the contribution of the negative Dirac spectrum to the average values of physical quantities and to the transition amplitudes. The basis is supplemented by the Dirac-Sturm orbitals, which are the solutions of the Dirac-Sturm equations corresponding to the negative Dirac spectrum. So obviously this leads to a doubling of the single electron basis, and the basis obtained in this way satisfies the kinetic balance conditions. The first step is, in order to construct the orthonormal set of single electron functions and to enable the subsequent use of perturbation theory, because perturbation theory is how we check the calculation, then we use a transition from the Dirac-Stuck basis, Dirac-Stuck basis to the Ruthin orbitals. The fifth step, when we move further, is the calculation of the physical quantity described by the Hermitian operator in A, and we use their Hellman-Feynman theorem. And actually, we kind of reduce this task for the easy calculation, and we reduce it to the calculation of the atom in the external field. And this leads to the, but the problem when you simplify the calculation in this way, this could lead to the violation of the symmetry of the external field. But how we can cope with that? Normally, how we cope with that, we use the orthonormal single electron basis constructed using by the unrestricted Dirac-Fock-Ruthin method. The next and the final step, we use the concept of restricted active space. It's a set of non-relativistic configurations, and we construct them in such a way that they, they will avoid the overlapping of the wave functions. So here we go. To implement the configuration interaction method and the many particle perturbation theory, it is necessary actually to first build the basis of single electron functions as our step number one. How we get them? Of course, we take a look at the easiest Breda approximation, and the multi-electron system is described by the Hamiltonian in this way. And so here is the this part is the non-local Dirac-Fock potential, and you can choose many of them. We actually have our paper where we tested like 20 of them and we derived the better one. I'm not talking about that today, but next time probably. The problem that the spectrum of the Dirac-Fock operator, this one, includes the continuous spectrum, and the contribution of which to the correlation energy can be 60 or 70%. And you can imagine what kind of impact that could cause on the system. In addition, the average radius of the excited bound states grows rapidly with increasing of the principal number n, which is logical. There, when n is 1, it's close to nucleus. The 2, 3, 4, 5, so it becomes bigger and bigger and bigger. So the wave function becomes too long. And so these orbitals are purely adapted to take into account and the correlation effects of the ground and low excited states of atom and ions. Imagine if you take these wave functions and you have 4, 5, or 7 electrons, so it's absolutely impossible to calculate them all at the same time. So one way, there are different ways to work with that, but the easiest way, and once you calculate something in the computer, you're always searching for the easiest way. So the easiest way to eliminate the states of the continuous spectrum is to actually place this particle in the continuous infinite box. So for neutral ions, the radius of this box should be 20 to 30 atomic units. In this case, to obtain the high precision data, it is necessarily to include on the order of 30-40 radial basis functions for each value of the relativistic quantum number kappa. This is actually quite obvious to imagine that is leading to a very large, over 2,000 number of single electron functions. Of course, such a large single electron basis cannot reasonably be used in the calculations by the computation methods. So that's why here we use the Sturm orbital basis, and we give them a virtual states, and it helps us to avoid these disadvantages. So here is an explanation of what's happening with the, you see, as the principal number n grows 1, 2, 3, 4. The function behaves differently, but actually it doesn't give you any good and positive calculation in your system. So we need to move forward from the, that's why we move from the Dirac-Fock. This is the Dirac-Fock orbitals. We move to Dirac-form Sturm orbitals. And so here is 1 electron energy that we take. Here is a Sturm function, and we use the weight function. We use the simple weight function, the simplest ever, but what we want to obtain is that once r goes to infinity, obviously the wave function comes to 0. And so it helps us to obtain the Dirac-Sturm function, because the operator doesn't have a continuum specter. They form a complete basis set, and Dirac-Sturm orbitals have approximately the same size, which doesn't depend on the principal number n. And so you see, we shift from this image to this image. Then what is the restrictive area active space? We actually use the set of the Slater determinants, which is included in the expansion of the multi-configuration wave function. Of course, if we talk about the interelectronic interaction, wave function is multi-configurational, and it is obtained by generating all determinants from a given list of non-relativistic atomic configurations. Actually, this list of this configuration is constructed by single, double, triple, quadruple excitations from one or more reference configurations. So the restrictive active space 0 actually corresponds to inactive occupied cores. They are frozen core. This space includes orbitals from which excitations are excluded from consideration. So there are no excitations. So restricted active space 1 corresponds to occupied cores or closed shells. This space includes orbitals for which the number of excitation is limited in RS2 and RS3. So restricted active space 2 is actually an active space. It's active inhabited valence orbitals. This space includes unfilled shells, of course, because if we talk about valence electrons, they're unfilled shells, and vacant shells whose energies are close to the energies of the valence shells in the Dirac-Fock-Sturm method. So, and the last but not the least, restricted active space 3. Here we talk about the vacant inhabitant, unfilled or highly excited orbitals. And the DFS method, the Dirac-Sturm orbitals belong to this space. So that's where we work. So this is a brief representation of the method itself. And let's talk a bit about what do we achieve with that. So one of the most exciting calculations, we had many of them that I worked on. We worked together with a theoretical group of National Institute of Standards and Technology in US and the experimental group of Francesco Furlano in Austria. And we were calculating the hyperfine structure of laser cooling transition in the fermionic erbium 176. Why we were doing that? Because actually experimental groups started to pay a lot of attention to the lantanides with the submerged 4F shell. Because they have a submerged 4F shell electrons orbital, and they are used in the ultra cold quantum physics. And the success of this quantum, actually we call it quantum degenerate gazes, the success of their use in experimental physics comes from properties as energy levels, hyperfine structures, and atomic polarizabilities. And so the only problem is that erbium only have so the good part of the erbium is that it has 6 stable isotopes, so they are quite stable and we can work with them. But to perform the magnetical optical trap, there is only one isotope, there is only one fermionic isotope that we could use. So it's erbium 167, this one. And because why it poses the problem, because the bosonic isotopes, they have a 0 nuclear spin, while the fermionic has a very good one, and it has a split on many levels. So what we have measured there, we have measured and analyzed the hyperfine structure of 2 lines. Here is one, the yellow one is 583 nanometers. The blue one is 401 nanometers. And of the only stable fermionic erbium isotope. And we were focusing on the transition from the J to J+1. And we were cooling the transition, actually that's the ground state of xenon. And respectively, we obtained the, as I introduced earlier before, the hyperfine structure. So we were able to, at first define experimentally and then to prove theoretically the A and B constants for this unknown previously known line, but unknown constants for this line. So in the other words, why also these Lantonian gazes are so important, because these species, they can have a very strong magnetic moments, and they are magnetic moments, they're equal to 10 Bohr magnetons. And this is a key property for study of for the dipolar physics and for the performance of the magnetical optical trap. So let us move slightly further. So actually, that is what we got from the experiments. From the experiments, we got this this black line, and then we the black solid line, it was the recorded line. The red line actually is a simulated line shape obtained using a nonlinear fit to the line position. And it was made by it was simulated line shape. Actually, it was some of the, if you want to know more about mathematics of the first derivative of several Lorentzians. And for each hyperfine transitions, we're calculated the possibility of constants. And the realization of magnetical optical trap of harmonic airborne isotope was challenging always, because no one knew the A and B constants. And we were very lucky enough to at first to tune it in the properties they were supposed to do, and then to actually find the AB initio, we call it AB initio constants A and B for this for both, actually for both transitions. So we calibrated our system on the known transition line on the 583, and we saw a very good correspondence with this with the experimental data. And then so we used the same for the ground state as well, but it was much easier. And then we helped the experimental group to obtain the A and B coefficients for constants for the line of 401 nanometers. And it actually, for the future use of magnetical optical trapping. So this is shortly is. Let me conclude what we were talking about today. So firstly, I introduced you to the world of why our calculations are important, and why it became almost a fashion now because of the magnetical optical trap and ultra cold physics. Then I introduced you what is G factor, what is the hyperfine splitting structure. Then we also talked about the problems of the calculations of interelectronic corrections, because the more particles we have, the more corrections we have to the energy lines, because not only particle interacts with the nucleus, but particle also interacts with different particles, and so the energy shifts and splitting becomes different. So then I introduced you to the Dirac-Fock-Sturm method and to the computational interactions method. And I explained you how it works, how we avoid the negative Dirac spectrum. And then I also showed you how we change the shape of the wave functions, and how we avoid the dependence of Dirac-Fock functions from the principal number n, and we obtain Dirac-Fock-Sturm orbitals. And the last but not the least, in the theoretical, from the theoretical point of view, I explained how we cut the tails of the wave functions to avoid the interlapping in between of them. And after these theoretical presentations, I showed you how we actually work with experimental groups and our recent results and achievements. So thank you very much, everyone, for listening to me. Just brief representations of our team and collaborators. And please ask your questions if you have any.
Thank you very much for the very interesting talk.
I tried to be really on time, so follow the schedule.
Right. There was one question by Professor Balcheva, who is actually traveling, so she can't ask the question herself. She asked, could you please specify how do you calibrate the configuration integration method, calculations to obtain accurate results for 2 photon exchange QED corrections?
This is actually a very interesting and important question, because of course, when we talk about the computational methods, it's sometimes even the best theoreticians, they start to calculate one thing and then they shift to another, and then they never know how to prove their results, because you couldn't go too far from that. So what we do actually, for example, if we talk about the G factor, actually this term, the first term, is one photon exchange correction, and it's on the order of 1Z, and it is actually possible to calculate it analytically by the perturbation theory. So we at first we used to exercise, now there is a table of the different groups exercise these equations, and there are known data for these corrections. And we calibrate our calculations on this known data, and then we actually make a step forward analytically and numerically, and we calculate the 2 photon exchange, 3 photon exchange corrections.
Okay. Are there any questions from the audience? I have a question. I think you mentioned earlier that you use machine learning as well in a similar context. How do you use machine learning in this context, and what kind of machine learning do you use?
In this context, we mostly use the multi-configurational calculations that we were actually even performed that's many years ago, and they are made on Fortran. So it's mostly calculated on Fortran. When we talk about the machine learning and AI applications, we mostly use them on not on these specific topics. These topics, they're mostly about the numerical computational calculation, but we use it on healthcare applications. But
okay. Thank you very much.